So basically, recommender systems, as we all know, the problem is that we're given some observed preferences from users to items like movies. And the goal is to predict the unobserved preferences as accurately as possible. And unfortunately, usually we're given a very sparse rating matrix. So therefore, we usually would rely on the content information of the items. Like in the context of movie recommender system, it will be plots, directors, actors, and even the video themselves. Now, in order to model these content information and extract features, we have at least three options. We can manually craft the features. We can automatically learn the features using deep learning, or we can automatically learn the features using deep learning and adapt for the ratings at the same time. And naturally, the last options would be the best one. Unfortunately, although deep learning can readily produce powerful features and representations for subsequent tasks, it usually works only for independent data points. That means there will be no correlation between users and items, which is naturally not true for recommender systems. Therefore, in order to address this problem, we first formulate a probabilistic formulation of deep learning, modern deep learning techniques like graph neural nets or multi-layer perception. And then we extend it from independent setting to non-independent setting. And we call this framework that we propose collaborative deep learning. By doing this, we have at least two challenges. The first challenge is that we want the deep component to be some probabilistic deep learning models that are compatible with the graphical components and powerful, or at least as powerful as its non-probabilistic counterparts. And the second challenge is how to connect these deep components to the graphical components to actually model these similarities and preferences and perform the actual recommendation. So let's talk about the first challenge first. And we will start with a simple autoencoder. And usually this autoencoder is just some multi-layer perceptron where we have the content feed into the model, and it will go through several layers of linear, nonlinear transformation to recover the content itself. And usually we will use the output of the middle layer as the representation for the content. And these kind of autoencoder structures typically used for extracting features in an unsupervised setting. So you might be tempted to directly use these learned representation and plug it into the graphical component, but this would not work because it's not probabilistic, it's deterministic. Therefore, it's not going to be compatible with the deep component and the graphical component. So this is why we designed a probabilistic autoencoder. The difference between the standard autoencoder and the probabilistic autoencoder is that we transform the output of each nonlinear transformation, which is originally a value, into a Gaussian distribution center at that value with some level of noise or variance. And from now on, we will use this figure to represent the probabilistic autoencoder. And we use the conventional graphical model notation. We use the shaded circles to represent observed variables. We use transparent circles to represent latent variables and parameters to learn. And J here is the number of documents or number of items. So now that we have handled this first challenge, the next one is how to connect it to the graphical component to perform the recommendation. Now, let's start with this probabilistic autoencoder. We're going to start with this middle layer representation, and we will generate the latent factor for each item Vj from a Gaussian distribution center at this representation. And similarly, we can generate the latent factor for each user I from a Gaussian distribution with zero mean. And finally, we can generate the rating that user I gives item J from a Gaussian distribution parameterized by the inner product of their corresponding vectors. Now that if we already define this kind of graphical component, and given this component, given these documents, the X and the ratings R, we can infer the latent variables, including V and U, and then we can use the V and U to make the prediction for the unobserved ratings or preferences. And here is the overview of the graphical model. These lambdas are just some hyperparameters to control the variance of the Gaussian distribution. And recall that we have this overall Bayesian deep learning framework. We have a deep component and a graphical component. Correspondingly, we have this probabilistic autoencoder as the deep component. Note that internally it's just a simple probabilistic deep learning model with some linear, nonlinear structure. And we have this blue part as the graphical component to handle the relations between users and items and the ratings. And these two parts actually they're trained end-to-end and boost each other's performance. And besides graphical models, we can also see this model from a neural network point of view. In particular, if we take this lambda x, the Gaussian distribution variance, to infinity, our model will degenerate into simultaneously learn true neural network with common output, with common input and different output. And in the information flow will go both ways. It will flow from the ratings to the content, which means the content is actually adapting to the ratings. It will also flow from the content to the ratings, which means that the learned representation are actually used to boost the recommendation performance. And in a word, representation learning and recommendation actually happens together and benefit from each other. And in order to evaluate our methods, we use 3 datasets, 2 from Site You Like and 1 from Netflix. For Site You Like, we use titles and abstract as the content, and for Netflix, we manually crawl the movie plots from IMDb and use them as the content. And we have 2 evaluation metrics, recall M and MAP, and higher recall MAP indicate better performance, of course. And this is the recall M for different methods in one of the dataset. M here is the number of recommended items, and the vertical axis shows the recall. As we can see, CTR and deep music are the best baselines. And here CTR is just some shallow graphical model that combine matrix factorization and latent derivative allocation, LDA. And our method can significantly boost the performance. Note that this is already a very large improvement. And this margin gets even larger when we consider the sparse setting, when we only have very sparse ratings. But why would this happen? This is because when the rating is sparse, the accuracy will rely more on the quality of the representation from the content, which happens to be at the advantage of our model. And this is the MAP for different methods. We have also very promising results. We have a relative boost comparing to the baselines of about 50%. So how does this accuracy transform to actual revenue? And it's estimated that in Amazon, about 35% of the revenue actually comes from the recommendation. That means about $62 billion per year. And if this is true, then 1% boost of recommendation accuracy can actually lead to about $600 million of increase in revenue. Of course, this is just some very rough estimate, but you can see the scale here. And besides quantitative analysis, we also have an example user as a case study. In particular, we asked this user to watch the movies one by one, and we will also ask the baseline method and our method to recommend movies for this user. As we can see, at first, this user watched 2 movies, Moonstruck and True Romance. Note that these are both romance and drama movies, so naturally both methods will recommend some some romance and drama movies for this user. And at this point, the precision is 20% versus 30%. And as the process goes by, this user watched 2 more movies, Johnny English and American Beauty. Note that this is very different movies from the last 2, because these are action and drama movies, which indicates the user's interest has already changed. And our method is able to sensitively capture this change and recommend both action, drama, and romance movie for this user, and boost the performance, the accuracy from 30% to 50%, while the baseline fails to do so. And this is the result after the user watch and liked 10 movies. So to briefly summarize, we have designed a new probabilistic formulation for deep learning models and use it as our deep component for the Bayesian deep learning framework. And it subsumes the deterministic deep learning model as a special case. And we also have the first hierarchical Bayesian model for deep hybrid recommender system. And we're the first to do this end-to-end. Experiments show that we can significantly outperform the state of the art in different kinds of recommendation settings.